I'm Marina. I'm going to talk today, come on, stay, about this talk, Your Containers Aren't Alone, Demystifying Container Isolation. So first, a little bit about me. My name is Marina. I'm a research scientist at a company called Edera that does hardened runtime for containers. I'm also the co-chair of the CNCF, the Cloud Native Computing Foundation's Tag Security and Compliance. So I do a lot of stuff around security of CNCF projects and kind of work in security in the community more generally. I'm also a maintainer of TUF, a CNCF project, and before this I got my PhD in kind of this supply chain security space. So let's talk a little bit about multi-tenency. Why does container isolation even matter? So multi-tenency is basically when you have a bunch of different containers from different organizations or different users of an organization, like maybe different customers of an organization, all running in different containers but on the same infrastructure. And this is great because our containers provide a nice little box for us to contain our code, and you can then save resources because you're only paying for your set of the machine that you're using. You're not paying for a whole machine just to run your one workload. Unfortunately, because these containers are all on the same infrastructure, if you do nothing else, and we'll talk about things you can do later, then they're all kind of operating sort of like processes on the same kernel, which means that if you have somebody you don't trust, one of these other users of the system, in a different container, they might be able to get out of this container and look at your processes. And if you don't do anything else, they're just able to do this, right? You'd be just able to look at the process IDs of other things on the system and do that. So obviously this is bad, and what we want to do is we want to put stronger boxes, or what we call isolation, around our containers so that this doesn't happen, right? So that you can securely run things in this multi-tenant space and get all the benefits of running things in containers. Why is this important? I won't go into detail about these, but there have been problems, of course, with the lack of container isolation, or problems with or CVEs that have happened when this has been broken, which has allowed attackers to break out of containers and gain access to either the host system or other containers running on the system. And so that's just kind of a bunch of examples of why this is important, why we're talking about this today. So, container isolation. There's a bunch of different mechanisms for isolation. They include application and service isolation, runtime isolation, node isolation, as well as hardware and physical isolation. And we're getting to a couple of different examples of each of these. They kind of just operate at different levels of the stack, at different levels of isolation, to provide isolation. This thing really doesn't like me today, I'm sorry. There we are, application and service isolation. So this is our first category we're going to talk about. And I'm going to go over these very briefly, just for the sake of time, but these are a bunch of different technologies that operate kind of within the Linux kernel to provide something more like isolation around your container, right? Because on its own, the container doesn't do it, but if you add things like namespaces, cgroups, setcomp, capabilities, and SE-Linux or AppArmor, all of these work in different ways to provide kind of like access, so the different resources are seen differently by different containers, right? So if you have specific files, specific capabilities, specific anything like that you want a container to access, the combination of all these technologies kind of gives you an isolated view. Obviously, they each do individual things, but this is our summary. And so because all of these technologies operate kind of at the Linux kernel level, they're all kind of features of the Linux kernel, basically, that have been created to make containers work and be better. Some of those CVEs that we looked at before can actually still affect these different technologies, right? Because they're in the kernel, a flaw in the Linux kernel can lead to a flaw in some of these systems. And there still is this shared kernel underlying the whole thing. So you're kind of like layering some pieces. But the benefit of a lot of these technologies is that they're very lightweight, right? Because they're just working in the kernel, you're not adding kind of more layers to it, just kind of little pieces, little views. They can be really lightweight and really, really powerful for applications where speed is important, and maybe it's okay to have a slightly more security risk depending on exactly what the situation is. Next, we're going to talk about runtime isolation. So these are ones that operate kind of one step below. gvisor is kind of the exception of the group, so we'll start with it, which it provides what's called a user space kernel. So on top of your kernel that has your containers, you have this other layer that's gvisor that filters a lot of things through that gvisor layer, which provides like a really powerful barrier. So more so than just having these features within the Linux kernel, this is another piece that operates kind of at the user level to provide a filter between these different things. And so this, and I consider this a type of runtime isolation because it kind of operates, again, like on top of the kernel. The next pieces of technology I'm going to talk about kind of go one step even beyond that, where it's actually separating the kernel that the different things are running on, so that each container actually has its own version of the kernel. So the kind of the first way to do this is to think about a virtual machine. This is kind of a simplified example of how a virtual machine works. You have the hardware, you have a hypervisor, kind of operating on your host operating system. You have a virtual machine monitor. Some people consider this part of the hypervisor, but this is the piece that actually like manages the virtual machines. And then you have guest operating systems and your applications. Traditional virtual machine technologies are not very lightweight, right? They're designed for you dual booting your computer, for you testing things on different systems. And this is a lot of overheads that you can now run. You know, you're basically spinning up an entire operating system plus some stuff in order to run your one application, which is maybe a little bit silly. And so some people thought about this and came up with this idea called micro VMs. And what a micro VM does is the stack looks a lot the same. The difference is kind of subtle. It's that kernel at the top is now a microkernel, right? It's something smaller than the full kernel. And there's also some optimizations that various people have done at these lower levels, which I'll talk about very briefly, to make this all faster. And so this lets you run a lot more VMs on the same machine, kind of lowering that startup time overhead. It's still not going to be as fast as just using some of these Linux techniques for isolation of your containers, but you get a full separate kernel for the different containers or the different nodes, you know, running several containers, and that can be very powerful when this strong isolation is needed. So I'll talk very briefly about the hypervisor level. This is like the very bottom of this stack. You have the Zen or KVM. These are probably the two most popular hypervisors that are out there. KVM is a module within the Linux kernel, so you still have kind of the Linux kernel as your host operating system. KVM is within that, and it lets you have access to this feature on modern CPUs that's called, I'm sorry, that's that feature on modern CPUs, which the name is totally blanking my mind right now, but it basically gives you virtualization. Virtualization pass-through, so you can access the CPU and memory. Does someone have the name of this?
Rings, like the...
Oh, no, sorry, the name will come to me, but no, it's not that. But basically gives you pass-through to give really efficient virtualization on your different machines. The tricky thing about KVM is that because it needs this CPU pass-through, if you're running KVM on top of a cloud, so if you're like using a cloud provider to get your computer, they're already doing virtualization, potentially using something like KVM, and so you have to make sure that they're actually passing through those features, which is why I mentioned them in the first place, right? So you have to make sure that you have CPU pass-through, like full hardware access to the CPUs to use it, which is kind of one of the reasons I mentioned Zen, which is the other popular one, which also supports those features, but has what's called, one second, para-virtualization. And where para-virtualization means that you don't need that hardware access to the CPUs. And it's still supported by most guest operating systems on top of that. So that's kind of the difference there. Is that your question?
I was going to say about virtualization. Essentially,
yeah, okay, yeah. Yeah, exactly. So that's kind of why I mentioned Zen and KVM here, especially in the cloud context. On top of those, Firecracker just supports KVM, so I've put that in my diagram. But you need a virtual machine monitor. So the couple of popular ones for the cloud that I'll mention, and I am focusing here on kind of open source technologies. There's a lot of stuff out there, but it's an open source conference, so here we are. So Firecracker is developed by AWS. It runs AWS Lambda and Fargate in the back end. It's known for its like fast startup time for virtual machines. Cloud Hypervisor is another virtual machine monitor designed for cloud, slightly different performance characteristics, also optimized for cloud. On top of that virtual machine monitor layer, you need a container runtime, right? Because what we want to do, this talk is about, is isolating our containers, right? So on top of these virtual machines, we want containers. And Kata Containers is a container runtime that's designed for this environment. So it kind of operates at that level and is optimized for this. So that's kind of like the basic stack of the micro VM architecture. There's a couple of kind of variants that I'm going to talk about really quickly. The first is unikernels. This is maybe a slightly odd one because it doesn't actually natively support containers. I think it's the only one in my talk that doesn't. But it's an interesting technology where you kind of remove a lot of these layers of the stack that we have here by kind of compiling together your kernel and application. So you have like a very, very mini kernel that just has the stuff you need for your particular application, which makes it very lightweight, but a little bit hard to develop and use because you have to recompile the kernel, right, every time you're changing your application. But this is really nice for especially like embedded type spaces or other very specific spaces where that performance matters. Another interesting one is Hyperlight. So there's this thing called WASM, which basically has a user space sandbox for code. And then Hyperlight is basically a VM technology, a micro VM technology for running WASM applications in a sandbox at the hypervisor level as well, right? So yeah, quick summary of our runtime isolation. This gives you in most cases, you get a separate kernel per container. gvisor is an exception. They kind of do this user space kernel thing. Also very cool, but not quite a separate kernel. And you have but in comparison to the previous set of technologies we talked about, there is some additional kind of overhead and complexity issues with developing your code, with running your code. So just something to think about, but you do get that kind of additional isolation. And in some cases, you have hardware requirements or things you have to think about in terms of hardware, and you can't just be like purely in the world of software. I'm going to very quickly mention this. This is like another way you can get isolation. It's not so much a technology as it is a method, which is basically you separate your different nodes onto different machines. You have your containers on the nodes. This does get you similar isolation, but you kind of lose a lot of the benefits of containers because you can't actually pack your nodes together if you're separating them all in this way. But I think it's worth mentioning because if the overhead doesn't matter as much, this is a really easy thing you can do to get isolation, right, if you're just doing something small. And finally, a quick mention of some hardware methods. The one I have a slide for is confidential computing, which folks may have heard of. This is a very, very high-level overview of what that is. The basic idea is that you have something that looks a lot like our micro VM stack, but the container itself, instead of just running on the kernel, it runs on what's called a trusted execution environment, which is like a hardware chip that sits on or next to your CPU, depending on the architecture. And it supports things like encrypted memory and encryption of the application in use. So all the data of the application is encrypted in use on this specialized piece of hardware. This gives you incredibly strong isolation because not only are your containers isolated from each other, you don't even need to trust your guest operating system or your host operating system or your cloud provider or anything like that. You're really just trusting this one piece of hardware, which is very cool, but you do need access to, of course, the piece of hardware. And so this can be costly at scale depending on how many of these you need. And another thing in the hardware and physical space, which I'll give a quick shout out to, is an air gap, which of course is kind of the gold standard of isolation, where you run different versions of your application kind of like physically separate from the rest of the internet. So you really can't have any data leakage because there's no communication channel between them. But of course, this also has some complexity issues and some overhead. Here's a quick summary. I think I have 1 minute left, so I won't go into too much detail, but that's the different technologies we talked about. And I do want to take a quick moment here to ask you all to get involved. So I talked here about a bunch of different open source technologies in the container isolation space. In my role in CNCF tag security, we're definitely interested in getting a community together around this issue. So if folks are interested, or have other ideas that I missed here, or interested in any of the things we talked about here, definitely interested in chatting and figuring out how to make some guidance around what these technologies are, who should be using them when, and all that sort of stuff. So thank you all for coming. I don't think we have time for questions, but I appreciate all of you.